Hello, everyone. Welcome back. A happy Friday, Friday period 5-6. I hope you guys are watching this. Quick one today. We were meant to do maybe 6 pages. I'm going to cut it shorter and give you 2 pages. Reason for that is we are slightly in front of everyone else. Plus, I don't want to overload you with too much content without me being there. So we'll catch back up on this stuff next week. So week 4. Okay. What we are doing today, all right, is just going to be, it is tricky. Okay. So I would like you to focus. Don't think it's easy. It's a tricky concept. All right. But something that I find really, really enjoyable. So hopefully you guys find some enjoyment out of this. I'm going to share my screen. Okay. And I'll hide this, get my CAS, and in a second, now we are good to go. So hopefully you have got your unit book, page 135, please. So can you all go to page 135? All right. Again, I'm going to reiterate the point of this is so that you're still learning in a good manner, even though I am not at school today. All right. Um, and please rewind, pause, do what you need to do so that you understand what we are learning about. Today, we are just going to do binary matrices and something called permutation matrices. We will look at communication matrices next week, all right, when I'm back with you, most likely on Monday. All right, so let's get into binary matrices. Now, similar to bicycle, what else starts with BI? Um, oh, my brain is cooked. All right. By means 2 options, I guess, or two. All right. The 2 options in a binary matrix, it's a special type of matrix that only has 0 and 1 as elements. Okay. So some examples of binary matrices are these, I guess, the most common two would be this one, which is known as an identity matrix. Okay. And I guess this one would be known as a zero matrix. Okay. Nice. So you need to know what a binary matrix is. It's just a matrix that has 2 options, being 0 or 1. Now, I guess kind of by definition of having 2 options, you would say this is a binary matrix as well. However, binary matrices only have these. Okay, so no, this is not a binary matrix. All right, a permutation matrix is a square binary matrix where there is only one number one, okay, in each row and in each column. Okay, so in each row, we look at these two in the rows, 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 rows. There is only one in each row. Okay. Then if we look at columns, there is only one in each column. Okay. They do not have 2 1s in a row or in a column. Okay. So that is what a permutation matrix looks like. All right. And its use is to rearrange the elements in another matrix. So what it would do is grab something maybe that's in the first position and pull it to another position. Okay. It is used to rearrange elements in matrices. All right. Permutation matrices can be pre or post multiplied depending on the order. So whatever is needed, that is where it can sit. So what do we have here? Given this and that, find BA. So I guess what we might do, okay, is let's define these. So we're going to say A, A, B, 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 C, C, C. And I want to store this and we'll call it A. All right. Why is that? Maybe let's try. What if we call it capital A? Unless the Kaz just not happy. No. I'm not sure. Maybe it doesn't like the A's, the B's, and the C's. All right, let's have a look at this. Find B, A, and discuss your observation. So we're going to do B times A. All right. It'd be a 3 times 3. All right. We could do this is a permutation matrix. Okay. It's going to change the order of something. So if we do B times A, we're going to change the order of A. Now, position 1, 1. We're going to grab row 1 from B times column 1 from A. The only thing that matches is the 1 and the B. So the B would go here. Okay. Then if we did row 1, column 2, row 1 times column 2, the only thing that would be a B. If we did row 1 times column 3, which is this position here, the only value would be a B. Then we can do position 2, 1. So row 2, column 1. All right. The only thing that would match up is an A. All right. If we did row 2 times column 2, it would be an A. If we did row 2 times column 3, it would be an A. All right. Then if we did row C and column C, row 3, column 1, row 3, column 1. Okay, the only thing would be a C. Row 3, column 2 would be a C, would be a C. What have we noticed here is that these two swap positions, okay? And I guess the reason why they swap positions is because of how this matrix is set up, okay? What we notice is these guys here swap positions. Now, if there was a 1 here, a 1 here, a 0 here, and a 0 here, what matrix have we made? That would be called the identity matrix, okay? Now, if we did the identity times A, nothing would change. But if we start swapping around the rows, as we have here, that is where you can see that, the rows change positions. We'll get into an actual example, all right? What I'd like us to do is actually do this kind of by hand. Okay, so this is a 5 by 5 matrix, and this is a 5 by 1. It is defined, okay, the outcome is a 5 by 1. So it's going to look like this, all right? Position 1, 1, okay, row 1 times column 1. Row 1 times column 1. If we drove our car in and drove it down, the 1 would be on top of the P. All right, so I guess the first value would be P. Okay, row 2, column 1. If we grabbed our car and drove it in, the 1 would be on top of the A. So it would be PA. All right. If we then did row 3, column 1, and drove our car in, all right, the 1 would match with the L. So it'd be PAL. All right. If we did row, what do we got? Row 4, column 1, okay? The 1, and we drove it in, the 1 would go on top of the E, okay? And last but not least, if we did all of this, we got row 5, we drove it all in, the 1 would go on top of the S, okay? Now, you can obviously do this in your CAS, and it will tell you the answer, okay? What it's done here is it has rearranged the order, okay? So, if we had have done this as, if this 1, 1, 1, 1, 1, this is called the identity. If we did the identity times by a matrix called LEAPS, what would the outcome be? Leaps, okay? But we wanted to change it around. We want to get pails first, or we want pails. So we want P to be first, A, L, E, and S, okay? Now, the P is in the 4th position. So what we would change our first row is to have a 1 in the 4th position. We then want an A next. The A is in the third position. So we'd change our row to have a 1 in the third position. We then want an L. L is in the first position. We would change our third row to have an L in the first position. All right. We then want an E. E is in the second position. All right. And then we would have an S. S is in the fifth position. Now, there's only one row, one per row and one per column. This is a permutation matrix. What we've done here, we've just made what the example was, but we've looked at why that is the case. All right. Matrix P is a 4x4 permutation matrix. Matrix W is another permutation matrix. The matrix product results in the entire first and third rows being swapped. Okay, so PW works. Okay, we want to find P. Okay, now if I wanted nothing to swap, if I wanted absolutely nothing to swap, I would multiply by the identity. All right, if I wanted nothing to swap, this is what I multiply it by. It doesn't change. Okay, but we have said we want the first row and the third row to swap. Okay, we want the first row and the third row to swap. So what we're going to do is put the first row of our identity in the third row. Okay, and the third row of the identity in the first row. All right, now what that's saying is these bad boys here, the first and third have swapped, but the second and fourth will stay the same. Is there a matrix that looks something like this? All right. I'm happy with B being our answer. Okay. Now, a lot of the time you're going to be able to use your CAS. Sometimes you have to create a permutation matrix, which is kind of what we've done there. What I'd like you to do is start with the identity and work around and look at which rows are changing positions and go from there. Okay. Matrix P and W are defined. Okay. Now we start with Astor. Okay. That is what we start with. All right. And if we multiply P by that, P by Astor, it'll change. Okay. So if we just did P by Astor, row 1, we'd start with a T because we're looking for the third position. All right. Then it would be the fifth. So it'd be TR. Then it would be the second, TRS. Then the fourth being O. And then the first being A. All right. So if we used permutation, that is what we would get. Now, the rule that they have said to us is that we can raise the power of P so that P changes, and then it will, if we multiply it by W, we might still get our initial value. Okay, so let's go ahead and find what that value of P might be. We need to do a 5x5 matrix. All right, it's going to look something like this: 0, 0, 1, 0, 0. All right. 0, 0, 0, 0, 1, 0, 0. 0, 1, 0, 0, 0, 0, 0, 0, 1, 1, 0, 0, 0. All right, this is P. If we did this to if we square it, what might happen if we multiply it by a 5x1? All right, so 5 rows, 1 column. All right, and if we used A, S, T, O, R. All right, if we square it, it becomes Sarot. Okay. What if we cube it? So squaring it won't be Astor. Okay. What if we go ahead and cube it? Instead of Sarot, it's Sratoa. Okay. What if we do to the power of 4? Astor. Okay, so this is the value or the matrix we would like. Okay, so if we did the permutation to the power of 4 times the initial, we would still get back to where we started. Okay, that is all we are going to do today. All right. I'll put up the questions I'd like you to do, and then I'll also ask you to do additional questions on all topics. Use this as basically a revision lesson. We haven't done a whole lot of work, or this isn't a whole lot of content, okay? But I would like you to be fully confident with everything we've learned by Monday. All right. And we'll get into some communication matrices on Monday. All right. Then we have dominance, transition matrices, and we are nearly done from there. Okay. Remembering that the assessment is on the 30th of May. That is a Friday. Okay. Cool. Hopefully you guys have had a good week. I hope that if you needed to speak to me, okay, you would have emailed. But if not, I hope we're going well. So good luck. See you guys soon. Thank you.